I'm Andre Platzer, and this joint work with Yonghyun Tan is on differential equation invariance axiommatizations, which gives you a very elegant, purely logic-based way of proving all true invariants of differential equations and disproving all false invariants of differential equations. But we'll see more as we go. The setting is that of hybrid systems, which have fixed laws describing the state evolution with both discrete dynamics coming from control decisions and continuous dynamics modeled by differential equations, for example, according to the motion of the robot in an environment. The concept to study these is what I call differential dynamic logic, in which, for instance, you have a formula that characterizes that you are not collided yet and your brakes work. And if that's the case, then all runs of a hybrid systems model written down as a hybrid program are such that the robot doesn't collide in the states that it reaches later on, either where the robot first follows some discrete dynamics and then some continuous dynamics along a differential equation, for instance, where the position is changing continuously according to velocity, the time derivative of position equals velocity, while the time derivative of velocity equals the acceleration, changing continuously, and the acceleration is under discrete control, coming from the discrete controller, for instance, which is a process that repeats. And there is no way to understand hybrid systems without understanding the differential equations that are part of that, which is the topic of this talk. The classical approach is that whenever someone gives you a differential equation, you solve the differential equation and then analyze the solution. And of course, that does enable you to understand the behavior of the differential equation, but that entirely misses the point that the entire descriptive power of differential equations is that a differential equation is much easier than its solution. So the point is that if you describe a system using a differential equation, then you typically do so because describing the solution would be much more complicated. After all, the solution is describing the global behavior of the system, and that can be very complicated, while the local behavior described by the differential equation is still fairly simple. The classical approach is that when you're given the differential equation, you analyze the differential equation by first solving the differential equation and then analyzing the solution of the differential equation. That, of course, informs you about the analysis of the differential equation, but the difficulty is that this process going that way around undoes the entire descriptive power of differential equations because, hey, differential equations are much easier than their solutions. Even if you have a very complicated solution, which after all is describing a global behavior of a system at every moment in time, you can often still describe this by a fairly simple differential equation because a differential equation only describes the local behavior of the system. And now, Henri Poincaré already observed this in 1881 when he called for the qualitative theory of differential equations, analyzing differential equations by really analyzing the differential equation itself instead of going by an analysis of their much more complicated solutions. What this talk is about is it completes an important step in Henri Poincaré's enterprise by developing the logical foundations of differential equation invariance. It identifies axioms for differential equations, out of which completeness for differential equation invariance can be derived completely syntactically. So the fact that every true invariant can be proved from these axioms. In fact, every false invariant can also be disproved from these axioms, where the axioms on top of that are fairly simple, uniformly substitutable axioms and not infinite axiom schemata, so everything is fairly easy to implement in theorem-proving land, and you can overall decide the invariance just by logical proof. So let's get started. The concept of differential and dynamic logic that we need for this talk is just for differential equation properties. For instance, this differential dynamic logic formula here says that whenever you start inside the green region, then always when you follow this differential equation plotted here in the dynamics, right? What the differential equation does is circling around or circling outside, then always, when you start inside the green region, you will forever stay in the green region. And that's true, but it's fairly subtle. Like, look at this point here, for instance. It looks like the system might almost be coming out of that region, which would be violating the property. What's much easier to see is the second differential dynamic logic formula, which expresses that if you start on anywhere in the circle, then you will always stay anywhere on the circle when you follow the exact same dynamics. But both of those, of course, deserve a rigorous proof of correctness rather than just us staring at pictures. So how can that be done? Well, in differential dynamic logic, you have two components. The one is the hybrid programs, which describe the motion and behavior of the system over time, out of which for us the only important part today is the description of a differential equation, x prime equals f of x, or a differential equation system, within an evolution domain constraint Q. So a logical formula Q, which restricts how long we can follow the differential equation. Before Q stops being true, you have to stop following it. Think of it this, for instance, for putting time bounds. And differential dynamic logic formulas start out like logic does, with comparisons of, for instance, polynomial terms, knots, ands, quantifiers over the reals for all x's and there is an x, and most importantly, alpha box and alpha diamond modalities, where for any hybrid program formed like this, for us only differential equations matter here, and for any differential dynamic logic formula P, does alpha box P say that all behaviors of alpha is such that P is true in the end? And remember, differential equations could stop at any moment in time, so that means P is always true along alpha, whereas alpha diamond P means there is a way of running alpha to a state where P holds true. So there is a way of following a differential equation such that some fine day in the future P will be true. This differential dynamic logic is axiomatized. Here are the axioms. For instance, the most naive axiom about a differential equation is that always after running a differential equation x prime equals f of x is p of x true, if and only if for every time greater or equals 0 that you insert into the solution of the differential equation. So if y prime of t is f of y, then if you plug the time t into the solution y of t and then do a discrete jump to the new value x, then if p of x is true under all of those circumstances, then of course p of x is true always when following the differential equation, because it was a solution of the differential equation. And in fact, the entire family of solutions of differential equations. But that's hopelessly naive, because in a technically precise sense, almost no differential equations have good solutions that you can then do something about the universal quantifiers of. But still, this axiomatization is a sound and complete axiomatization of hybrid systems relative to either differential equations or also relative to the discrete dynamics. And that means the entire reasoning principles can be reduced to just proving properties of differential equations, because proving continuous systems turned out to be constructively proof theoretically the same as proving hybrid systems, and turned out to be constructively proof theoretically the same as proving discrete systems. But that, of course, makes it more interesting to prove properties of differential equations, for which there are the following logical principles. Here is a plot of the right-hand side of a differential equation. So plot the right-hand side with a vector in to which direction the system is evolving. And then, for instance, if the system is starting here, then it would follow that red curve. Always follow the right-hand side of the differential equation indicated by the vector chain. And of course, if you want to show that you never entered the bad blue regions, you could hypothetically do so by starting a system in each and every one of those infinitely many points, computing a solution at each of those infinitely many points, check the solution at each of those uncountably infinitely many points in time, and whether they ever entered the bad blue region, you know that the system is unsafe. If they never do that, you would know the system is safe, but you would need an uncountable amount of patience. Instead, differential invariants look at the direction into which the system is evolving. And if the system is ever evolving toward and into the bad blue region, then that would be unsafe, because the system could follow that. But intuitively, if it never does so, If the system only ever goes from safe to safe and safe to safe and safe to safe, then intuitively, I guess it always remains safe. The subtle part, of course, is that induction in differential equations land is super subtle because there is no next state in differential equations. Differential cuts are the logic principle that if you know that your system can never enter this red region, you can cut that out of the state space. And having done so, you might even learn more and be able to prove that you also can't enter the other red region, cut it out of the state space, and conclude that the system is obviously safe because it ran out of bad blue regions. Differential ghosts are another logic principle, the most spooky one, where the analysis of a differential equation x prime equals f of x may be sometimes difficult, and it shockingly gets easier by introducing more differential equations, by seemingly making the problem more difficult, by adding out of thin air, dreaming up the differential equation y prime equals g of x, y for a differential ghost variable, one that wasn't there before. But if you do that in a very clever way, then the relationship of the old system dynamics compared to the new system dynamics enables you to read off new invariants that were not there before. And if you do that in an even cleverer way, then you can even read off from those invariants properties of the original dynamics. For instance, this one always stays above 0, but it's kind of a miracle that it does, and the differential ghost is helping us reason how, in what way it's being held up. This is a little bit like dark matter for proofs. There is a behavior in the observable universe that did not make energy invariance balance out, but if you hypothesize something that you just can't see, namely the dark matter, and speculate on its evolution, if you do that in a clever way, then the observable and unobservable parts of the universe balance out to generalized energy invariance. Only unlike in physics, in proofs, it doesn't matter whether the y prime ghosts actually exist. Pictures are good, but proof rules are better. Here's the proof rule for differential invariance, where a property is always true after the ODE if it was true in the beginning, and you reduce that to differential reasoning, where you form differentials of the logical formula coming from differential terms whose meaning in an isolated state defined as the spatial derivative. So the derivatives of the values of the term itself by all the variables multiplied by the values of the co-state. That makes it possible to reduce a differential equation's property to a discrete shadow that instantaneously merely assigns the right-hand side of the differential equation to the left-hand side of the differential equation. Differential cuts accumulate knowledge, so they first prove a property C is always true after the ODE, and then edit the evolution domain constraint of the differential equation to assume that the system never leaves C. But that was a pseudo-restriction, because on this side you first prove that C can't be left anyhow. And then differential ghosts, where you reduce the property of the system to a bigger differential equation system. You add a new differential equation, y prime equals g of x, y. And if you do that in a way such that P is equivalent to the existence of a y such that G is true, then because P was true, you also know that G is true for some initial value of y in the beginning that you don't know anything about, and then as you follow the differential equation along the y prime equals g of x, y differential equation in addition to x prime equals f of x, then at the end of the day, by this premise, you still know that G is true at the end for some final value of y that you don't know anything about, but that's fine because as long as G is true for some value of y, P is true as well, which is what you wanted to prove in the first place. You can show that the deductive power is indeed additive. So differential cuts prove more than just differential invariance alone. And with differential ghosts, you prove more than with these two. But it is important for soundness of the differential ghosts that these differential equations actually have solutions that exist for long enough. For instance, if it's linear in the new variables, can have arbitrary higher degree in the old variables, but it should be linear in the new variables, then it has a solution that exists for at least as long as x does. Because it would not be correct to reduce the analysis of a very long-lived system to the analysis of a system that only has a very short-lived solution. A simple example is the damped oscillator, where you start inside the green region and will forever stay inside the green region. And the proof is not by analyzing the solution. The proof is by forming the differential of the post conditions. So you show that 2 omega square xx prime plus 2y prime is less or equals 0. And assigning the right-hand side of the differential equation to the left-hand side of the differential equation. which you can then substitute in and get arithmetic that very easily proves. This proof depended on the evolution domain constraint d greater or equals 0. Otherwise, the arithmetic wouldn't have worked out. If you have a similar increasingly damped oscillator where the damping coefficient is increasing, well, then a corresponding proof works out as well, where you first do a differential cut to show that the damping coefficient always remains greater or equal 0 if it starts greater or equal 0. Again, by a simple differential invariance proof is that easy. And then you can do the previous proof with arithmetic. If only you assume also in the beginning that the damping coefficient started greater or equal 0. Also keep in mind that you could actually repeatedly differentially cut in formulas to help the proofs. We gained the extra knowledge that d greater or equal 0 is always true by doing this proof down there, but you could gain additional knowledge by doing additional differential cut proofs. These are very simple logical proof principles for differential equations. The question is, even if they're very trustworthy because they're completely sound and rigorously proved sound, how far can you go beyond them? How much more can you prove with that? What are completeness thoughts on it? And it turns out that the differential dynamic logic proof calculus is also a sound and complete axiomatization of algebraic invariants of polynomial differential equations. So algebraic invariants of algebraic differential equations are decidable just by differential invariance, differential cuts, and differential ghosts in differential dynamic logic, the proof principles you saw. When you have invariant equations, for instance, or conjunctions of those or disjunctions of those, then these algebraic invariants are decidable for differential equations. And with a bit more thought, the differential dynamic logic proof calculus is also a sound and complete axiomatization of semi-algebraic invariants of differential equations, which are then decidable in differential dynamic logic. So also inequalities, knots, and all the other operators work out. All of first-order logic, real arithmetic. Soundness means that every proper you prove in differential dynamic logic is valid, so true in all the states. And completeness means that all the true invariants are actually also provable in differential dynamic logic, so you're not missing any. Let's develop this one step at a time. The first extension is to look at Taboo equalities, which have been introduced by Gaston Taboo in 1878, but really turn out to be just a derived form from differential ghosts. In order to show that a polynomial equation e equals 0 is an invariant of the differential equation, is always true after if it was true before, it suffices to prove that e is a Taboo polynomial. So its Lie derivative is a multiple of itself, where g is any arbitrary polynomial. Here's an example where this polynomial is always true after the differential equation that we already saw, if only if it is true before. And for that, it suffices to look at the Lie derivative of the polynomial, which gives you 2u prime plus 2vv prime, substitute in the differential equations later on. And that is a multiple, namely by this cofactor, of itself, of u squared plus v squared minus 1. And that proves that you indeed will always stay in the circle. Taboo equalities actually derive from differential ghosts, but rather than going into the proof why that works, I will later show you a more general proof, and simply instead observe that in fact an even stronger statement is true, that the Taboo axiom already derives syntactically from differential ghosts, namely that if always after a differential equation the differential of e is a multiple of e itself by some polynomial cofactor, then if e was 0 in the beginning, it will always stay 0 when you're following the differential equation. But let's already generalize it right away from Taboo equalities to Taboo inequalities, which ultimately stem from Thomas Grunwald's principles of Grunwald inequalities from 1919. Where if e is greater or equal to 0 in the beginning, then e will always remain greater or equal to 0. And also, if e is strictly greater than 0, it will always remain strictly greater than 0. And for that, it suffices to prove a Taboo inequality, namely that the Lie derivative of e is greater or equal a polynomial multiple of itself. And Taboo inequalities are not a new proof principle because they simply derive from differential ghosts. In order to see that, what we do is we introduce a differential ghost as a counterweight to e prime greater or equal GE, namely y prime is a fresh variable that wasn't there before, it's a ghost, that follows the differential equation y prime equals minus gy to reduce the analysis of e greater or equal to 0 to the question whether e times y is greater or equal to 0 and y is positive. Because clearly, if y is positive, then e times y greater or equal to 0 is equivalent to e greater or equal to 0. And then the remaining question whether y always remains positive is reduced by yet another differential ghost as a counterweight along z prime equals g over 2z to reduce the question whether y is positive to the question whether yz square is 1 as an invariant. And of course, if yz square is 1, y must have been positive all along. And both of those are constructed along with their various differential equations that they follow in order to make the remaining questions very easy. So the question whether yz square is 1 and whether ey is greater or equal to 0 are now simple differential invariants just by construction. For instance, ey prime is simply e prime y minus gye, but hey, e prime is greater or equal to gy by the assumption, and as long as y is positive, which you know by the first part of it, then this will always remain greater or equal to 0. In examples, here's the taboo inequality used in an example principle, and you notice that this expression, 1 minus u squared minus v squared, is always greater than 0, though you're always inside the circle as you're following along, but it's getting closer and closer and closer and closer to this distance 0, or plotted over time. The value of e is tending towards 0, but still e prime is greater or equal to g time e, so there's something that's holding up the value. And that's all it takes to introduce a differential ghost as a counterweight, y prime equals minus gy. That will make ey greater than 0 always true. And that still leaves around the second question, what about y? But y greater than 0 can also be shown by introducing a counterweight, z prime equals g over 2z, in order to reduce the question to a provable invariance of yz squared equals 1. In a bit more detail, e is greater or equal to 0 reduces with the differential ghost to the same question with an additional differential equation in it. That reduces by monotonicity to proving the two conjunctions. That reduces by a differential cut to first prove that y is positive, and then assume that y is positive, which makes the left conjunct trivial, of course. And they're constructed exactly such that the remaining differential invariance is under arithmetic. It's really easy. On the second branch, they're constructed such that after the counterweight, z prime equals g over 2z is an extra differential ghost, is it easy to prove that yz squared is 1, which of course implies that y is positive, but differential invariance is under corresponding real arithmetic. What you've learned from that is that taboo equalities and taboo inequalities can be used in a sound way because they derive completely syntactically from differential ghosts. But in order to generalize this, something that we call vectorial taboos can also be used soundly because they derive completely syntactically from differential ghosts. A vectorial taboo is an entire vector of polynomials that is 0. In other words, their conjunction is 0. If their conjunction is 0 in the beginning, then that vector or their conjunction is always 0 at the end. And for that, it suffices to prove that the vector of Lie derivatives of E is a multiple of E itself, except this time it's not a multiple by a single polynomial, it's a multiple by an entire n cross n matrix of polynomials when n is the dimension of the vector of E. And that, again, is not a new reasoning principle that needs to be trusted, but it merely derives completely syntactically from the simple atoms of reasoning of differential ghosts. And the idea is sort of like before. You introduce a counterweight of y prime equals minus gty, only this time it's an entire vector of differential ghosts in order to change the question whether e is 0 to the question whether e times y is 0. But then the trouble is that even if e times y is 0, that does not imply that e is 0, even though you know that y isn't 0, because that merely implies that the vectors of terms e and y are orthogonal to one another. Now, the idea is to simply do that again by introducing more differential ghosts, for instance, an entire time-varying matrix of differential ghosts, y prime equals minus yg, done in such a way that y times the original vector of terms e is always 0. And then indeed, if ye is 0, then e must have been 0, provided the matrix is a regular one, which can be shown by proving that its determinant is non-zero, which it will always be by another differential cut after proving that its Lie derivative satisfies a Taboo equality relationship. So the determinant of the matrix is a multiple, namely by the trace of the matrix of itself, and the trace of the matrix is a polynomial expression whenever the matrix is a matrix of polynomials. Intuitively, you can think of this as continuously performing a change of basis that balances out the motion of the expressions. And why such a continuous change of basis is even sound as well, because it simply derives from differential ghosts. In fact, in similar ways can you show that an axiom for vectorial Taboo equalities is also derivable. Here's the idea. So for illustration, you have a dynamics that's very complicated, but if you introduce new differential ghost variables that describe new coordinate systems, if you will, with a changing coordinate system, so first looking this way at this point, then later on looking that way at this point, and so on, then because your coordinate system keeps on evolving in a very clever way, you can do that in a way such that the actual coordinates of the point always remain the same constants. And of course, constants are invariants of every dynamics. And because you've linked it back and forth with differential ghost arguments, that does imply that the original properties were also invariant, which is kind of using another principle of Henri Poincaré, which Wheeler put in his mouth as characterizing that time is defined so that motion looks simple. You look at the evolution of the system from a different perspective. Likewise over here for that dynamics. Now, this is one way of proving vectorial taboos are differential ghosts, but you need an entire matrix of differential ghosts. It is actually also possible to do this with just two differential ghosts, which is of course much more parsimonious. Only in that case, I don't have an equally easy intuition for you to share with that I can visualize. But it does work by a proof using squared Frobenius norms, which are compatible vector norms with an Euclidean norm. And then do a subtle proof to show that the resulting arithmetic with differentials actually does prove. But the point is, in any case, that vectorial taboos are a trustworthy proof principle because they simply derive syntactically from differential ghosts. And once we've got that, you can do a lot more, because that means that what we call differential radical invariants are also trustworthy proof principles derived simply syntactically from differential ghosts. The proof principle is the following, that always after an ODE is an equation E equals 0 true. For that, it suffices to show that E is 0 and its Lie derivative E prime is 0 and its Lie derivative E double prime is 0. So all the Lie derivatives are 0. All the way up to a Lie derivative such that the next Lie derivative, the nth Lie derivative, will simply be an algebraic combination of the lower Lie derivatives. Well, because intuitively, if you're at the point where all the Lie derivatives are 0, then, while there's motion, hopefully there isn't that much motion off the circle, which is of course subtle if you're not dealing with analytic ODEs, which this generalizes to. But differential radical invariants followed syntactically from vectorial taboos by introducing the vector of higher and higher and higher Lie derivatives of the term, E, the first Lie derivative, second Lie derivative, and minus last Lie derivative, and a matrix which simply has ones on the off diagonal to say that the Lie derivative of E, well, that's 1 times the second entry, sure. The Lie derivative, here's another 1, right? The Lie derivative of the first Lie derivative is 1 times the second entry, which is the second Lie derivative, and so on. And the only interesting part of the matrix is that the sum of all of those Lie derivatives multiplied by the corresponding cofactors is indeed the Lie derivative of the last one, which is the nth Lie derivative. So it derives completely syntactically. And the point is that the left-hand side is now a finite logical formula in differential logic that characterizes that all the Lie derivatives of E are 0. mnemonically written E prime star, but it's a finite formula characterizing that all Lie derivatives are 0, thanks to the second condition that the next Lie derivative would be an algebraic multiple of the lower Lie derivatives by some polynomials. And yeah, intuitively, if these are all 0, then those also should be 0, and it stays that way forever. And the point is that such an n actually exists by a consequence of Zorn's lemma, namely that all ascending chains of ideals are finite in the Noetherian domain, such as this one. And this arithmetic formula now tells us that E is always 0. You can do something like that for inequalities as well. So for semialgebraic invariance, the easiest case is, in order to show that E is always greater or equal 0, you show corresponding conditions that significant Lie derivatives are compatible with that. So the most significant Lie derivative is greater or equal 0 whenever E is greater or equal 0, and if E is 0, then the most significant Lie derivative of its Lie derivative is greater or equal 0, so recursively going down. So, while the most significant Lie derivative is strictly positive whenever E is strictly positive, or if it's 0, then at least the most significant Lie derivative of its Lie derivative is positive. And these recursive formulas actually are finite thanks to this fact, that ultimately the Lie derivatives will be an algebraic multiple of the lower Lie derivatives, which means E prime star will be 0, and if that's the case, then E will always be 0, which will enable you to tell apart the case whether E is greater or equal 0 from the case whether E is positive, strictly. The intuition is as following. You keep on forming higher and higher Lie derivatives, but in a sound, very syntactic way, so nothing can possibly go wrong, to argue whether P prime is still 0, so then it's inconclusive, or P double prime is still 0, then it's inconclusive, or finally P triple prime is the appropriate sign, so you're moving inside the set rather than accidentally leaving it. But notice that this is fairly subtle, because there's some point on this dynamics where it's getting pretty close, so proofs are always important to do this right. In order to syntactically derive those reasoning principles, by far the easiest way is the following to adopt the unique solutions axiom, that if you can follow a differential equation x prime equals f of x within the region Q1 to a point where P is true, and you can also follow it within the region Q2 to a point where P is true, then because solutions of continuously differentiable differential equations are unique, the P must have happened here already. In other words, it was possible to follow the differential equation x prime equals f of x within both Q1 and Q2 to a point where P is true. And in fact, vice versa as well. This is an equivalence. Continuous existence axiom that says that within the open region where E is greater than 0, it's possible to follow a differential equation that has at least some motion, so for instance a clock variable, to another state where even if x was equal to y in the beginning, it is no more, if and only if E is currently positive. Well, because if you're in the middle of the region where E is positive, you can follow the differential equation for at least a short amount of time to a different state where E is still positive. So solutions exist and the behavior is continuous existence axiom. So if E is currently positive, it remains currently positive for a little while locally. So you can follow the differential equation solution for a small amount of time to get to a different state without having left E greater than 0 yet. Because the value of E is continuous, it cannot drop from positive to 0 instantaneously. And then the real induction principle, which says that always along a differential equation x prime equals f of x is P true, if and only if, for every point that we could leave the region, for every point y that we could leave the region. If we are at this point y, well then first of all, at the end of this, P is still true, so we can't have left for an open boundary, but also P is still true for a little while longer, so we can't have left at a closed boundary, and that real induction principle is also an if and only if characterization. And there's another cute one, which is the differential adjoint principle, which it was used in the Noetherian back again axiom of differential dynamic logic already. So x can go forward to y along x prime equals f of x within q of x, if and only if y can go backwards to x along y prime equals minus f of y within q of y. Forward motion and backward motion are adjoints to one another. And from these simple principles, can the real induction rule be derived syntactically in the most eloquent way, to simply say that P is always true along a differential equation, because locally P still remains true for a little while longer, so we can't have left at a closed boundary, but also backwards, P can't have become false all of a sudden when we're working backwards. So if P was already false, looking back, it was already false for a little while. So we can't have left for an open boundary. And this local progress modality is definable in differential dynamic logic as follows, by saying that if we remember the current value of x in a fresh variable y, then if we follow x prime equals f of x within P, except at the point where we're currently at, then we can go elsewhere, somewhere where x is no longer y. So locally you can follow within P for a short moment of time. From these principles, can you syntactically derive useful induction principles for local progress? For instance, if E is greater than 0, then E remains greater or equal to 0 for a short moment of time, because, come on, E can't have dropped from positive to negative without time passing. But also, if E is currently 0 and its Lie derivative E prime remains greater or equal to 0 for a short moment of time, then E itself remains greater or equal to 0 for a short moment of time. And that gives us an induction principle. Because if you can't prove this, but E is 0 at the moment, then you need to look at the higher Lie derivatives and ask it about locally remaining greater or equal to 0, which you can do that repeatedly, again, accumulating the knowledge that E prime must have been 0. Do that again to accumulate the knowledge that E double prime must have been 0, or always the cases where they already have more significant signs. Ultimately, when sufficiently many of the Lie derivatives are 0, then the differential radical invariant principle captures that E must have been 0 all along. With this, you can derive the local progress axiom that if the local Lie derivatives are greater or equal to 0, remember here it is, that implies that indeed locally E is greater or equal to 0, and likewise the most significant Lie derivative being strictly positive, reminder here it is, does indeed show that locally E greater than 0 is true for a short moment of time. And you can staple that together to have a characterization of a local progress condition for semi-algebraic formulas, where P prime star is defined by a homomorphism out of the formulas, which is hard to prove why that's correct, but P and Q has a local progress condition of the local progress condition of P and the local progress condition of Q, and the local progress condition of P or Q is the local progress condition of P or the local progress condition of Q. And that gives you then an if and only if, that local progress is possible if and only if some arithmetic formula is true. And since local progress formulas were what we were interested in the real induction axiom, and this rewrites in arithmetic the local progress principles that remain from the real induction proof rule, giving you rise to the following two completeness theorems. Algebraic completeness, the differential dynamic logic proof calculus, is a sound and complete axiomatization of algebraic invariants of algebraic or polynomial differential equations, which are decidable with a derived axiom, the differential radical invariant axiom, namely that, for simplicity for open sets, x prime equals f of x within Q has the property that in the future E will always be 0 if and only if at the moment the evolution domain constraint implies that all the Lie derivatives are 0. Remember, this is a finite formula. And this equivalence characterizes all future behavior of the differential equation, future truth of an equation by current truth of a transformed equation. Because it's an equivalence, you can equivalently reformulate future truth of an equation with current truth of arithmetic in an if and only if, and thereby prove it with real arithmetic quantitative elimination if and only if it's true, and disprove it in real arithmetic quantitative elimination if and only if it's false. And the entire thing was complete logical syntactic rewriting because it was a derived axiom. With a bit more thought, you can also show that the differential dynamic logic proof calculus with the real induction axiom, etc., is a sound and complete axiomatization of semi-algebraic invariants of differential equations, so even with inequalities, greater equals, and so on. These are decidable with a derived axiom. This time it's also an equivalence, but a bit more complicated one. that indeed for all x's is, so P is an invariant of the differential equation if and only if the local progress condition P prime star is implied by P, and backwards as well, so meaning the local progress condition for the backwards dynamics x prime equals f of x of the negation is implied by not P. This generalizes also to a sound and complete axiomatization of analytic invariance of analytic differential equations with the same differential radical invariance axiom, and a sound and complete axiomatization of semianalytic invariance of differential equations by a corresponding derived axiom, where terms can be extended way beyond polynomial terms by augmenting it with function symbols, with the only conditions being that these function symbols have smooth interpretations, that the partial derivatives have a syntactic representation, so the partial derivative by the variables is also a term, and that they have computable differential radicals, so it's possible to compute numbers n and extended terms gi such that the nth Lie derivative with respect to any analytic differential equation is a combination of the lower Lie derivatives with, again, extended terms. In fact, these conditions are satisfied for Noetherian functions, where a function is a Noetherian function whenever it's a polynomial applied to the variables and the values of functions forming a Noetherian chain on the variables, where a Noetherian chain is a set of functions that are real analytic, and the partial derivatives of the functions is a polynomial applied to the Noetherian functions. For instance, sine, cosine, and exponentials are like that, because the partial derivative of sine is the cosine, and the partial derivative of cosine is another polynomial, namely simply minus sines. The two of them together you can take, but one of them in isolation you couldn't take because you would be missing the syntactic representation of its partial derivative. And the partial derivative of the exponential function is simply the exponential again. And since Noetherian functions satisfy the smooth partial derivative and computable differential radicals and conditions, you inherit completeness for differential Lemming logic with differential equations that are using Noetherian functions in the invariants and in the differential equations. Summarizing, what you've seen is differential Lemming logic in action, developing the logical foundation for differential equation invariance, and thereby completing an important step in Henri Poincaré's call for the study of the qualitative differential equations. You saw a complete axiomatization, not just sound where everything you prove is true, but also complete where everything that's true has a proof, of algebraic invariance of differential equations and analytic invariance of differential equations, where even future truth was provable equivalently, and semi-algebraic invariance of differential equations, as well as semi-analytic invariance of differential equations. What you saw generalizes to algebraic hybrid systems decidability. So equational properties of algebraic hybrid systems are decidable. You have a complete characterization of local progress properties. This can be decided by differential Lemming logic proofs and disproofs, and everything follows from uniform substitution axioms. It's fairly easy to implement soundly in a theorem prover. It does extend to analytic terms, for instance, to Noetherian functions. When you think about it, what goes into this? These are fairly tame properties of differential equations. So all that goes into this, from proof principles, are differential invariants, which internalize the mean value theorem, differential cuts, which externalize the prefix closure of differential equations. Whenever you have a solution of the differential equation, the first part of it also is a solution of the same differential equation, just a bit shorter. Differential ghosts, which internalize the Picard-Lindelöf or Cauchy-Lipschitz theorem. The real induction principle, internalizing the completeness of the real numbers. The continuous existence axiom, internalizing existence. And the unique solutions axiom, internalizing uniqueness, which overall give you a very impressive power of differential ghosts, because that was underneath all of that. So you've seen fairly simple proof principles: differential invariance, differential cuts, differential ghosts, real induction, continuous existence, and uniqueness. From these very simple principles do much more sophisticated reasoning principles for differential equations derive. Taboo equalities, taboo inequalities, differential radical invariance, semi-algebraic invariance, the real induction principle, and local progress properties. More about the underlying proof principles can be read about in the Logical Foundations of Cyber Physical Systems textbook.